Hello IGCSEs. Oh look, it's that time of the day where the sun's just crept round and it's doing weird things. Hello! We are doing IGCSE. We're doing a whole IGCSE course, aren't we, over about 2 years, and we're in our second module. None of the modules relate to each other, so you can jump in anytime you like, and this is the electricity module. And I'm quite excited about this one because we've been learning about loads of different things, current and voltage and charge. We've had to learn quite a lot about what energy is. And today we're doing resistance, and this is like the last piece of the puzzle. Once you've learned about resistance, it's just kind of all the tools you need. Like I've been having to keep not saying things because you don't know them yet. And after this, I'm going to say what I like. So certainly for me, this is going to be a good lesson. We've been talking a lot about different models. A model is something that you use to explain how something works in science, and you need models for electricity because you can't see it, obviously, and it can be quite complicated. So there's different models. The first time I taught this course 2 years ago, all right, Dylan in the comments, I used this model a lot. I'm actually not really going to use this model at all, except for this bit. Because when you're revising, you might come across it. This is a very common way to describe electricity, but it's not actually the way that most people who are sort of physics teaching experts would recommend that you do it. But anyway, thinking about that, with that in mind, that this isn't really the best model for electricity, let's just get our brains working by doing a little bit of recap. So we've talked about electric current in the last couple of lessons, which is the amount of charge passing a point per second, right? Are you with me so far? Do we have to go back a bit? Are you all right? We've been talking about how inside metal wires there are protons, positively charged particles, yeah, and the protons usually have electrons whizzing around them, but in metals and stuff like graphite in your pencil, there are some electrons that are free to move, and if you make one side of the wire positive and one side negative, then the electrons will be repelled by the negative side and they will be attracted to the positive side. So basically putting something like a battery and looping a wire around it, batteries have got a positive side there and a negative side. So that makes the electrons flow, right? Which is what electric current is. It's electricity is charged particles flowing. So here we've got a model of, there's a hotel with loads of people in it, and the Science Alliance are going to the Globe Theatre in London. They're American taxis because American taxis are prettier. But anyway, we've got a hotel here full of people. It's chock-a-block on this very neat circular road leading from the hotel to the theatre and back again. There's taxis nose to tail. The taxis are collecting people from the hotel, driving them slowly to the theatre, dropping them off, and then going back for more people. We haven't looked at this before. Electric current is the amount of charge passing a point per second. Voltage is the amount of energy per charge. Yeah, you remember we did about that? Like the voltage of the battery is the amount of energy basically that the battery gives to the charges, and the voltage of the bulb is the amount of energy that gets transferred to the bulb. In this model of people being picked up from a hotel and taken to the theatre, taxis going back again, can you tell me, it doesn't matter if you can't, maybe this is your first lesson, in which case you definitely won't be able to, but if you've done the previous lessons, what in this model represents charge, what represents electrons, what represents energy, what represents current, and what represents voltage? And if you're feeling super fancy pants and you remember everything that we did last week, what represents EMF and what represents potential difference? If you're new, this will all seem horribly overwhelming and bizarre. Don't worry at all. I think it probably will become clear as we go on. But if you're not understanding it, it's not because you're not clever, it's because you just don't know it, and I'll tell you in a bit. I'll pull my blind down while you think on that. They were there were some mixed responses to this on Facebook. I was going to say not everyone got it right. That's not exactly wrong and right answer as long as you can justify it, because obviously it is a model. It's not actually how electricity works. Here we go. How have you got on? Should we go through it? This is just supposed to be a recap. It would be good if you didn't use this model, really. Well, current is the amount of charge passing a point per second. Voltage is the amount of energy per charge. So current is the amount of taxis passing a point per second, which makes the taxis charge. Now, you got to be careful here, right? Do you remember? We'll recap this again next week. Charge is measured in coulombs, distance is measured in meters, time is measured in seconds. The amount of charge on something, like the amount of charge on these protons or whatever, is measured in coulombs, but 1 electron is not 1 coulomb of charge. Do you remember this? 1 coulomb of charge is much bigger. It's like a whole packet of electrons. So if you said that the taxis are the electrons, that's maybe not quite right. But then again, we'll look at a different model, which is much, much better in a second. That's why you brought your string. So don't worry. It's not exactly about getting it right or wrong. It's just to get you thinking. I've said that the electrons are the parts of the taxi. The taxi is 1 coulomb of charge, and the current would be the amount of taxis passing a certain point per second. So maybe the electrons is like the door, and it's a packet of lots of different electrons in a charge. Not different ones, you know what I mean. The energy is the people, so the hotel is the battery, the theatre is the light bulb, the hotel provides the people that get taken to the theatre and then dropped off at the theatre, kind of in the same way that the battery provides the charge with energy, so the electrons, the packets of electrons have energy, and then they transfer that energy to the bulb. The current would be the taxis passing a point per second. The voltage is, if the energy is the people, the voltage is the amount of people per taxi. So a really high voltage hotel, a really busy hotel would give loads of people to the taxi. A really small hotel wouldn't give very much. You can see why this model doesn't really get recommended, can't you? If you came last week, EMF, the electromotive force, is how much push the battery gives the charges. It's how much energy really the battery gives to the charges. So the EMF, the electromotive force, would be like the amount of people that the hotel puts into the taxi, if you like. And the potential difference we learned last week, don't worry if you didn't know that, is it's the amount of energy actually transferred to the bulb. So the potential difference in this model is like the amount of people who get out of the taxi, I suppose. And if there were 2 theatres, maybe half the people would get out of that in that theatre, and then half the people would get in. Anyway, can we please? Because hopefully looking at that, hopefully, hello Bastian, good to see you. Hello Ruby. Hopefully that model will at least make you appreciate how good this next model is that we're going to look at. Have you brought a piece of string or rope with you? If you have, can you please tie it so that it's in a loop? What we're going to do is, you've got to be a little bit careful, especially if your rope is thin. But what I want us to do is to stretch out a leg. Be really careful, because when you're pulling on the rope, if you've got a thin rope, you could really give yourself like rope burn on your toes. So be super careful, please. But this is what I'm modelling for you. So I've really stuck my foot in your face. This is what I want us to do. Get a piece of rope over your foot and give it a little pull like that. Just put the rope between your hands so that the rope travels around. Believe it or not, this, I think, and the Institute of Physics thinks, because they told me, is a much better model for electricity. Why? What's going on here? What's the current here? What's the voltage? What's the charge? So voltage is, we said that there are a lot of different ways of talking about voltage. Voltage is basically the amount of push that the charges get, right? It's the amount of energy per charge. It's the amount of joules of energy per charge. So a 12-volt battery would give 12 joules of energy to each charge going round. A 2-volt battery would only give 2 joules of energy per charge. So it's sort of how much they're pushed, you can think of it as. So we've got something going round, just like current goes round in a circuit. So the current here is, we'll say that the charge is the rope, right? The charge is the rope. The charge is moving around our circuit. The current is just how much rope passes a certain point per second. So the current is, I suppose you could say how fast the rope is going, couldn't you? How much rope, say, passes my foot per second. The voltage is, have you said that it's the hands pushing? So it's how much energy the charge is getting. So if you push very quickly or very hard, be really careful of your skin, please, if you're doing this with the toe. If you push very hard, that would be a high voltage, a lot of energy per charge, just like the rope's got a lot of energy. And if you do a gentle push, not much energy per charge. But we can bring resistance into here as well, very beautifully. Because what resistance is, well, it is what it says really, it's the resistance to the flow of charge. Resistance is how difficult it is for the current to flow. So with the taxi model, it wasn't really any very good way of showing that. But with this model, I mean, again, I don't know if you actually want to do it because you've really got to be very gentle. But if you like clench the string between your toes and try and pull, you'll find that suddenly it's very, very difficult. You've made it harder for the current to flow. You've given the current, you've put more resistance into the circuit. You've put more resistance into the circuit, so it's harder for the current to flow. So you're having to push harder. We're getting ahead of ourselves. There's various things that can make it difficult for current to flow. There's various things that affect resistance. What resistance really is the little electrons in the wires colliding with things. So effectively, sort of colliding, they don't actually touch them, but kind of colliding with don't say the protons, because the protons, they don't touch the protons. And also there are electrons orbiting around these protons. It's not like all of the electrons are free. What do we say if we're writing this in IGCSE? I suppose you would just talk about the collisions in the wire, the collisions with the atoms in the wire. So the electrons are trying to flow, but they're bumping into stuff. They're colliding with things, is the proper word to use. And the more collisions there are, obviously, the harder it is for the electrons to flow. So the lower the current, the less charge per second goes by, because they're bumping into stuff, colliding with stuff. I'm going to keep saying bumping. Don't write bumping in your IGCSEs. We've talked a bit in the past about directly proportional relationships. If something has a directly proportional relationship, it means when one goes up, the other thing goes up the same. So for example, if you earn £10 an hour, the money you earn and the hours you work, that's a directly proportional relationship. If you earn £10 in 1 hour, if you double the amount of hours you work, you double the amount of money you earn. You see what I mean? Yeah. So you get proportional relationships like that. And you also get things called inversely proportional relationships, which is the opposite. So, quick, Lara, think of a inversely proportional relationship. Can you think of a relationship between two things where when one thing doubles, the other thing halves? Come on, could be really boring. I guess we could just do money again. Like, the more sweets you buy, the less money you have. If you buy double the amount of sweets, you've spent twice as much money. You've got half as much money. I'm just going to say that you know what I mean. I'm so sorry. I can't believe this has been saved on YouTube forever. What I'm trying to get to is, if I double the length of this wire, are there more collisions? Is it harder for the current to flow? Or is it easier for the current to flow? If I double the length of a wire, is there more resistance there? More collisions? Or is there less resistance? Fewer collisions? If I double the length of the wire. Just move on, they'll never notice. What do you reckon? So resistance is how hard it is for the current to flow. And current is the amount of electrons passing a point per second. Yeah, you've made it harder, right? There will be more collisions. There is more wire, so, well, the wire is longer, there'll be more collisions. You've actually doubled the resistance. If you double the length of the wire, then you double the amount of resistance in the wire. What about if I make the wire twice as wide? Like this. Now what's going to happen? She says, like you would know. No reason why you would know this. What happens if I double the thickness of the wire? If I double the area, we say, the cross-sectional area of the wire. Are you okay with what cross-sectional area is? So if this Play-Doh tube is a wire, then the cross-section area would be like if you cut it across that way, it would be the area of this bit. So I've doubled the cross-sectional area of the wire. What has happened to the resistance? Well, you probably guessed. I'm just going to move on. You've halved the resistance of the wire. The wider the wire is, the easier it is for current to flow. It's just got more space. It's quite similar to, I think this is a nice model. If you imagine lots of cars on a road, all getting all snaggled up, proper word for it, in the traffic. If you opened another road up, effectively making the road twice as wide, then the car would be able to go down that road instead, and the traffic would ease a little bit. It's the same sort of thing. You don't even need it to be a separate road, can you? If you make the road twice as big, then the cars can get round each other and the traffic will flow more easily. It's the same thing. So again, if you're doing the Cambridge specification, I don't think you need it if you're doing EdXL, but one of the people who might write your exam, you need to know that double the length of the wire, you double the resistance, double the cross-sectional area of the wire, you halve the resistance. Oui? Right, let's see if you've understood that. Let's just have a look at these little diagrams. Here we go. So I've just got circuit A here is super simple. It's just a cell and some wires and a little bulb. That's a symbol for a bulb, hot cross bun. Can you have a look at circuits 1, 2, 3, 4 and 5, which are a bit similar to circuit A and but not the same, and say, do they have more resistance or less resistance or the same amount of resistance as circuit A? It's quite hard actually. I haven't really told you everything that you need to know, but I think some guessing will be good for your brains because then it'll make you think about it. And then when I give the answer, you're more likely to remember it. This isn't a trick. Sorry, this is a mistake, not a trick. That should just be a regular cell. I've just accidentally missed off the short end of that cell, so that's not one of my classic mean tricks. So circuit number 1 is exactly the same as circuit A, except there's no bulb. Would it be easier for the current to flow or harder for the current to flow if there was no bulb in the circuit? Circuit number 2, you've got 3 bulbs this time instead of 1. Is it going to be harder for the current to flow or easier for the current to flow if there's 3 bulbs in the way? 3 is exactly the same as circuit A, except the wire is much thicker. 4 is exactly the same as circuit A, except there's an ammeter in there measuring the current. Ammeters measure current, which is measured in amps. And number 5 is exactly the same, except one little bit of the wire has got frayed, so is very thin. Would that make it that there was the same amount of resistance as circuit A, more or less? I'm going to get my hand lens out while you do that. How are you getting on, you done? I don't know if I'm really giving you enough information to answer this question, but I do like making you guess, although I hated having to guess when I was a student. Like, just tell me the answer so that I know, so that I get it right. Okay, well, really, to know the answer, you need to know what's going on inside one of these bulbs, which you might do, you might not know. I'm hoping you don't, because it's a good excuse. Well, no, if you do, that's fine, but we're going to just have a little look at this bulb through my hand lens, because my hand lens is just cool. There we go, look. So what can you see there? Inside one of my tiny little bulbs from my electronics kit, can you see there's 2 big bits of wire sticking up, but then there's a very small bit of wire in between those 2 bits of wire. You see that? So what that is a very, 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 very thin bit of wire. They don't make bulbs like this anymore. They won't be, well, they certainly don't have them in your house. They won't be in your house, I wouldn't have thought. But yeah, inside a traditional light bulb, you've got these 2 big bits of wire like this. And then in between, you've got a really thin wire, which is all coiled up. Why is it coiled up? It's to give it the most resistance you can possibly get. It wants it to be really hard for the current to flow through the bulb, because it's all those collisions between the electrons and the atom in the wire that are what give off the light. I mean, it's very inefficient. Basically, what it has to do is get very hot. And this is why wires do get hot. All these collisions cause a lot of resistance. Well, all these collisions generate heat. And the bulb gets so hot that it gives off light. That's like the whole point. It wasn't a great design. We've moved on. We'll talk about that later. But yes, it's very thin because the smaller the cross-sectional area of the wire, the higher the resistance, yeah? And it's very long because the longer the wire, the more resistance. So it was right for the time. But you really had to know that it was very difficult for current to flow through a bulb. Some of you will be looking back on this like, well, just give me another 2 minutes then so I can answer them again. So circuit 1, the resistance is much lower in that circuit. It's very, very easy for the current to flow. Do you remember ages ago we were talking about how a bulb being lit or not doesn't necessarily tell you if current is flowing? And I showed you a sort of circuit like this. So I've just got 4 cells here. I've got some batteries linked up to a bulb, which is shining nice and brightly. And I said, what's going to happen if I put this wire across here like this? And I didn't want to do it for very long because what happens is the bulb goes out, right? Oh no. Oh no. Oh, just blowing. Yeah, okay. That red light has come on because the circuit wasn't happy with this. The reason it wasn't happy with that is because there's hardly any resistance in that circuit. If I put that wire across there, it's really hard for the current to go through that bulb. So most of it is not traveling through that bulb. More of that next week. I've made it really, really easy for current to flow just through the wires and then straight back again, to the point where it's so easy that it's just a really, really good way of running down your battery because the battery just sort of does this massive push and then it's done. So yeah, don't build a circuit like that. You'll just run your battery down. Number 2, yeah, there we go. So number 2, the resistance would be higher. It's much harder for current to flow because you've just, in fact, it would be, we could put a number on that really, can't we? It would be 3 times harder for the current to flow than it would be in circuit A because you've got 3 bulbs instead of 1. Number 3, it's easier for the current to flow because this wire is much thicker. So the bigger the cross-sectional area, the easier it is for current to flow. Number 4, that would be the same because as we've talked about, ammeters are designed to measure current. So it would be doing a terrible job of measuring current if it affected the current. Ammeters are specially designed so they have a very, very low resistance so that they don't change the amount of current flowing through them. If they had a high resistance, not much current would be able to flow. And number 5, the resistance is higher. It's much harder for the current to flow. Whoops. Because it's a very, very thin wire, right? So the cross-sectional area of that bit is very, very small. So that gives the whole circuit a much, much higher resistance. Right. I touched on this here. I said that if the resistance is high, not much current can flow. We need to talk about this. This beautiful equation. We don't really get to dig into it properly with IGCSE, but this absolutely gorgeous equation, V equals IR. But let's try and feel the equation, kids, before we just look at it on the board. Have you got your string again, or your rope, or whatever, or your shoelace? So we have talked about this a bit. If you, again, please don't hurt yourselves. Please don't. It's really not good for my business if you hurt yourselves. But if you can, then if it is safe to do so, curl your toes up around your bit of string and then very gently try and push your string through. It's harder, right? So we've increased the resistance of our circuit. God, I don't do any yoga. I don't do enough exercise for this shenanigans. I'm going to halve it. We've made it much harder for the current to flow by clenching the rope. So what happens then? This model tells us beautifully what happens if we increase the resistance of a circuit. If we make it harder for the current to flow, if we increase the resistance, like by making the wires thinner, or more usually by adding more components like bulbs or resistors, we've made it that less rope passes a point per second, haven't we? So if we try and pull the same amount, if voltage stays the same, but resistance goes up, then the current drops. And that is what happens. So what do you have to do to make the current the same? If you've increased the resistance, if you're really clenching your toes and you've increased the resistance of your circuit, but you want the string to travel around at the same speed it was before, what have you got to do? Yeah, you got to increase the voltage. And that is what you have to do. And we sort of looked at that, didn't we, in the previous lesson? If you add another bulb to a circuit, you add another battery. To push them around more so that you get the same amount of current flowing. And the bulb lights up the same. Let's get it. That's a good model. So again, it's a beautiful relationship because actually if you make the resistance twice as big, you need twice as hard a push, twice as much voltage to get the electrons to flow around, the charge to flow around, I should say. So you quite often, you see it written like this. Do you remember that V equals current? Because physics hates us. So you see V equals IR a lot. But actually, that's not really the nicest way to write it in terms of how you explain, how you think about it. Because it's sort of more often, it's going to be the current which is changing because of what you do to the voltage and the resistance. So if we rearrange that equation, put the V on top, I think it's probably better written like that. Current equals voltage divided by resistance. So you know about dividing, don't you? If this number's really big, then this number gets really big. Yeah? So if voltage is really high, then current gets really high as well. If this number on the bottom is really big, this number gets small. So if resistance is really big, current is really small. And we don't have to say really big and really small because this is a directly proportional relationship. So if current, if voltage doubles, if you give it twice as much push, then the current doubles. And if resistance doubles, then the current halves. Yeah. I'm going to give you some questions. They're hopefully they're very straightforward. I'm not testing your maths. We've got all different levels of maths here. I'm sure before you do an IGCSE, you would revise some maths. So I don't want to test your ability to kind of manipulate numbers at this point. I just want you to kind of check that you've got the hang of this relationship, really. Oh, hello, Arthur. Right. Oh, yeah, I knew I'd forget to tell you this. What's resistance measured in? So voltage is measured in volts. Current is measured in amps. Resistance is measured in ohms. Fabulous word. And the sign for ohms is fabulous as well. It is the omega symbol, like that. So ohms is written OHMS because of Mr. Ohm. And that's the symbol for it. Yeah, good. Here we go. So please do not forget your units. Don't forget to write A or V or ohm after your answer. Ignore the resistance of the wires. It's absolutely tiny. It's usually negligible. So number one, the current flowing through a bulb is 2 amps and the voltage across it is 10 volts. What's the resistance of the bulb? I've even rearranged the equations for you. You definitely need to be able to do that for IGCSE. Current equals voltage divided by resistance. Voltage equals resistance times current. And resistance equals voltage divided by current. Make a note of something I need to tell you in a sec. Number 2, the voltage across a battery is 6 volts. The resistance of a circuit is 3 ohms. How much current flows through the circuit? Number 3, a resistor, that's just a component like a bulb. It's just something that you put in a circuit to change the resistance. A resistor has a voltage across it of 20 volts and a current of 5 amps flowing through it. What's the value of the resistor? Number 4, this circuit has 3 amps flowing through it. What's the bulb's resistance? And you've got a circuit here. Again, it's just a bulb and some wires and a 9 volt cell, sorry. And number 5, you add another identical bulb to the circuit in question 4. Next to the first one, what's the new resistance of the circuit and what's the new current? I'm going to stamp the comments. Oh, yeah, exactly. Yeah, Arthur, that is a good point about that model. Yeah, okay. We'll go back to the model because that's what I needed to tell you something else. Yes, that would be friction. Oh, this is nice. When I touch the screen, all the comments jump up. There's Dylan, who is ready for some science. Oh, that's nice. Lakila's saying, me? Oh, picture some popcorn, that's so good. Hello, Matt Moon. Bastian's here, Dylan's here, Ruby's here. All right, Alpha. Oh, hello, Particle. Does that thumbs up mean you finished? If you finish them, get your rope out again, and I've got 2 more reasons here written on the board that I need to remember to tell you. 2 more reasons why it's a good model. 2 things that are true of the rope model that are also true of an electric circuit. See if you can think of what they are. Can you think of anything we haven't said that is why this is a good model, just while other people are finishing off? In fact, I'll turn you around. So, hello, if you're watching on catch up, hello, I just turned around because you might not be listening to the audio, you might have skipped ahead. If you finish these questions, can you be using your rope to try and think of 2 other ways this is a good model? 2 things that this rope model does that a real life electric circuit also does. I'm about to tell you them after we've been through the answers to this. Oh, another one actually. Have I missed any out of them anymore? I've got sort of 3 now. I suppose there's another one. Okay, let's go through the answer, shall we? The current flowing through a bulb is 2 amps and the voltage is 10 volts. What's the resistance of the bulb? So, well, it's pretty easy, isn't it? You're talking, or you just check that the current is related to the bulb and the voltage is relating to the bulb, and it is. So the resistance is just the voltage divided by the current, which is 10 volts divided by 2 amps, which is 5 ohms, yeah? Number 2, the voltage across a battery is 6 volts. The resistance of the circuit is 3 ohms. How much current flows through the circuit? So again, we've got the voltage of the battery, the resistance of the whole circuit. So the current flowing through the circuit is voltage divided by resistance, which is 6 volts, divided by 3 ohms, which is 2 amps. A resistor has a voltage across it of 20 volts and a current of 5 amps flowing through it, so the value of the resistor must be 20 volts divided by 5 amps, which is 4 ohms. Number 4, if this circuit has got 3 amps of current flowing through it and there are 9 volts being provided by the battery, the resistance of the bulb must be 9 volts divided by 3 amps, which is 3 ohms. Question number 5, you add another identical bulb to the circuit in question 4 next to the first one. What's the new resistance of the circuit? Well, I said to ignore the resistance of the wires. So if the resistance of the circuit with one bulb is 3, if you add another bulb, you've made it twice as hard for the current to get through. So you've doubled the resistance. So it would be just 3 ohms plus 3 ohms, which is 6 ohms. And the new current, can you see that you could have worked that out 2 different ways actually? What's the new current? What is the new current? Well, you could have said the new current is going to be the new voltage of the circuit divided by the new resistance of the circuit. So you could have done 9 volts divided by 6 ohms. Or you could have said, well, the circuit did have 3 amps of current flowing through it, and then we doubled the resistance, and I know that we've made it twice as hard for the current to flow, so the current is going to be half. And either way, that would have got you to 1.5 amps. Okay, so Arthur leads us nicely to using this rope model again before we just do one last little collection of questions. Excuse me for getting my toes out once again. Yeah, one of the things that is so beautiful about this model is that the reason I kept saying be careful, be careful, be careful, is because what is the rope doing? It's transferring energy to your toe, right? Or transferring energy to your foot. Just like a battery transfers energy to a component. So you pushing like this, the voltage of your circuit is transferring energy to your foot. Yes, that is through friction, like two things rubbing together, so the string rubbing against your foot. And obviously that does generate heat in the same way. That's another reason this is a good model. That generates heat in the same way that these collisions generate heat, which is why you've got to be careful. Another reason this is a fantastic model is because can you think of anything you could do to make one side of the rope move faster than the other side of the rope? What could you do without sort of, you know, changing the basic premise of the model? What could you do to make one side of the rope move faster than the other side of the rope? There's nothing you can do, is that? There's nothing you can do, and that's the same. Next week we're going to look at series circuits and parallel circuits, but a series circuit is just a simple loop like this. So in any kind of circuit that is just a simple loop, there's no way, you can't have the current flowing more quickly on one side than you can on the other side. The current is always the same, those charges are always moving at the same speed all the way around the circuit, and it's exactly the same with this model here. What else did I have? So yeah, the current's the same in all different parts, just like it is here. We've got the friction, so the heat. Oh yeah, and I've said, again, only if you're doing the Cambridge specification, I think, we've been talking about EMF being the voltage of the battery and potential difference being the voltage of the bulb or the component or whatever. This model kind of shows you that they're not the same thing. You would think that they would always be exactly the same number, but they're not actually quite the same number because because there is resistance inside the battery actually. So the amount that you're pushing with, the energy is always a bit wasted. We need to do an energy lesson, but anyway, yeah, the amount that you push with, not all of the energy from your hand gets given to your foot because some gets wasted, dissipated around here, which is the same as a battery. More of that later. What if I put breaks it? Oh yeah, so if you were to break the circuit, if you were to break the rope, it wouldn't work anymore. It's a bit tenuous, that one. Right, should we do one last? I've just got like 5 questions here based on one circuit, and then that's the end of the lesson. Have a go at these. You've got another very simple circuit here. You've just got 2 resistors actually in series, just a loop of wire with 2 resistors, a 5 ohm resistor and a 3 ohm resistor. You've got an ammeter on the right hand side next to the 3 ohm resistor, which is showing a reading of 2 amps, and you've got a mystery ammeter on the other side next to the 5 ohm resistor, which isn't showing a reading. You need to tell me what that is. So can you please tell me what is the total resistance of that circuit? Again, ignore the wires. You always ignore the wires because they're negligible. What's the total resistance of that circuit? What's the reading on the second ammeter, the mystery ammeter? What's the voltage across the 5 ohm resistor? What's the voltage across the 3 ohm resistor? And so can you tell me what voltage that battery is? It should be a cell, shouldn't it? I know, it's just one cell. It's not a battery, but, you know, tell me the voltage across the cell, please. Shall I go through it? If you haven't got it, then you probably want me to go through it so that you can find out the answer. At least I'll go through it slowly, and then you probably get the last ones by the time we've done the first ones. The total resistance of the circuit is 8 ohms. You just add up all the different resistances all the way around the circuit. So the total resistance is 8 ohms. The reading on the second ammeter, I only just told you that, didn't I? Sorry. But yeah, the reading on any ammeter you put in this circuit will always be the same because it's just a looped circuit, right? So the current is always going to be the same all the way around, just like with our rope model. So the voltage across the 5 ohm resistor, well, you know that it's a resistance of 5 ohms because it says it on there, and you know that 2 amps are flowing through it. So the voltage is the resistance times the current. So it's going to be 10, not 1. Oops. Oh, wow. That's a poor show, isn't it? What's happened there? Oh, I know what's happened there. Wait. Sorry, that's just my office. Wait, come here. Wait. There we go. Oops. There we go. So 8 ohms, 2 amps, voltage across the 5 ohm resistor is 10 volts. So the voltage across the 3 ohm resistor is the resistance, which is 3 ohms times 2 amps, which is 6 volts. And the voltage of the battery, well, what is the voltage? The voltage is the amount of energy per charge. So if the charges have got 6 joules of energy per charge going through the 3 ohm resistor, and they've still, on their way out of there, got 10 joules of energy per charge to give to the 5 ohm resistor, then you have to add those up, right? Because energy can't just disappear, it's got to come from somewhere. So the voltage, the battery must be providing 16 joules of energy per charge, and it is. Is that all right? Or the other thing you could have done is, you could have said, okay, I know that the total current, the current of the circuit is 2 amps all the way around. And I know that the total resistance of the circuit is 8 ohms. So therefore, we can work out the total voltage as well. It would just be the total current of the circuit times the total resistance, which is 16 volts. See? Lovely. Right. So hopefully, I mean, there were sort of fairly simple questions that were designed to teach you how this all works. Hopefully, you're feeling a bit more comfortable now for going off to do some past paper questions, which will be a bit kind of more tricksy and interesting. I have updated the homework PDF, finally. So if you go to my website where all the printouts are available to download for free, then there's a button that says, like, if you go to my website and you click GCSE current, which is like the GCSE course that I'm teaching at the moment, as soon as you've clicked it, you get the kind of front page where there's like forces in motion and electricity listed. And there's a pink button there which says something like homework or download homework PDF. So if you click that, it takes you to Coffee actually, but eventually it takes you to this free. I've put it on my Coffee page, but it is available for free for everybody because I do not charge anyone anything for things that would help you pass your exam. It's hard enough to get an IGCSE physics, frankly, without me charging you loads of money for it. So I just say, if you can support me, please do. That is how this business model works. I'm going to go to Facebook and see if anyone's left me any comments, but actually, I think last week it was only Bastian using the comments, and Bastian is here commenting on the YouTube video, so maybe no one's left me any comments on Facebook today. But yeah, if you're watching live, oh, there are comments! Bastian, have you been multitasking? Who is this? You left the live chat on. Oh, hi, thanks, Jacob. Yes, I did. Hello, Jacob. Yes, if you want to support me, how it works is everything that I do is free, and I just say, if you value my work, then please pay me. That's the only way that I earn money. There's no like, oh yeah, the current IGCSE. Oh yeah, I see what you did there. I see what I did there. Yeah, there's no secret Zoom group. I keep getting asked if I do private tuition, and I don't really have time. You are my students. You are my only students. Just the comments that I get here is the only interaction that I have with my students, apart from the awesome photos that you send me and stuff. Anyway, if you want to support me, my students, then you can. You can go to my About section on YouTube, and that takes you to this website called Coffee, where you can send me £5 a month. Which hopefully, I mean, especially for IGCSEs, £5 a month is not very much for someone who is trained to teach physics and has a physics degree, teaching physics into the internet. So I hopefully it's working out for everyone. It's the best value IGCSE course that I've ever come across, but there's loads of you, so also equals a wage for me. I will send you nice things to say thank you. Oh, next week we're doing series and parallel circuits, and then there's a week off for half term. And then after half term, we will finish off electricity, and then we're doing waves. So if you sign up to support me now, I will send you some diffraction glasses which make you see rainbows, which is all very strongly linked to waves. I'll send you an explanation sheet I wrote for how they work. And I'll send you Theatre Science magazine. So these are past magazines which have already been and gone, but if you sign up to support me now, you will receive, if you sign up with £5 a month, you get the mould issue, which comes with a free biodegradable plastic bag so that you can do a growing mould activity and a comic and a choose your own adventure. It's super fun. I really love writing Theatre Science magazine. And if you sign up with £6 a month, I send you that and the sleep issue as well, which also has a choose your own adventure and a little origami koala, and it tells you a bit about what's happening in your brain when you sleep, and yeah, it's got a choose your own adventure and a beautiful jigsaw, which there's no answer to, you just have to work it out. Yes, thank you very much. Did you find out why I'm backwards on YouTube? Oh no, I didn't actually. No, I didn't search, I didn't Google it. I just sort of, as I usually do, went, oh well, what's happening now? I'll work around it. Yeah, haven't found out. But I'm assuming, I don't think it's any button that I've pushed. I think it must be a universal thing. But yeah, I should probably look it up, shouldn't I? It hasn't really made any difference, apart from I can't wear any clothing that has writing on it. Where was I? Yes, so thank you very much. Thank you so much if you're supporting me. Thank you for liking these. Thank you for subscribing. Thanks, Flynn, for saying that this was a fun lesson. Very much appreciated. And thank you also for your money, if you can spare £5 a month, because that is what makes this my job. Right, I'm going to go and, oops, because I need to charge my phone battery apparently. And yeah, just plan a whole new set of lessons for next week. So yeah, don't forget, homework PDF now available to download from my Ko-fi page for subscribers and non-subscribers, because my supporters are absolutely blooming wonderful people and really like that these lessons are available to everyone and like that they are helping to make them available to everyone. So thank you very much, supporters. I will see you next week.